good day. Our lesson 1 will be the chemical formula and the structural representations. Okay, so let's start with structural representations. We have different types of structural representations. It could be a molecular formula, structural formula, ball and stick model, or a space filling model. So I will be discussing when it is convenient to use a specific type of representation. First one, molecular formula. Okay, so molecular formula, it is a literal representation. So when I say literal representation, all you can see is a set of letters, just letters that correspond to the specific element or an atom. So it is convenient to write the molecule in a molecular formula. For example, is if you ought to write a molecule in a notes, so that is very convenient and very efficient. So next one is structural formula. So structural formula uses a letter that is connected by a line. So the letter corresponds to the element, and the line, so as you could see, we have here the line that corresponds to the bond, meaning for this case we have an H line and an H. It means that the hydrogen atom is bonded to another hydrogen atom. Another one, we have the hydrogen bonded to the oxygen, and the oxygen is also bonded to another hydrogen. Next one, we have this nitrogen, letter N, bonded to one hydrogen, the left side, one hydrogen on the another side, and one hydrogen that is written at the bottom. And the next one, we have methane. For example, we have a carbon bonded to a hydrogen, bonded to another hydrogen, bonded to another hydrogen, and bonded to hydrogen. So structural formula is perfect in presenting the bonding, or on what specific atom, in what specific atom does the other atom is bonded to. So we have here the ball and stick model. So ball and stick model, although it is more difficult to represent a molecule in a ball and stick model compared to structural formula and molecular formula, ball and stick model was able to represent the bonding of the atom, and other than that is the spatial orientation of each atom in a molecule. So for example, so of course we have this hydrogen bonded with another hydrogen, but it is as you can see on water, you can see that the hydrogen bonded to oxygen and then bonded to another hydrogen, their spatial arrangement is in a bent form, which is totally different with the structural formula. So as you can see in the structural formula, we represent hydrogen, the bond of hydrogen, oxygen, hydrogen in a straight line. So they lack representing the atom in a spatial orientation. So we have here the bent that is represented by the ball and stick model. Another one we have for the ammonia, as you could see, we can only see that the in structural formula, the bonding is in a planar form, just like a flat triangle, right? However, in a ball and stick model, we could see that one hydrogen, the hydrogen that is bonded to this nitrogen um, is in protrude, meaning it is coming out of the paper, coming out of the plane. Okay, so this one is in line with the paper, and the another one, the hydrogen, as you could see, we can define that this hydrogen is placed at the back of this molecule. Okay, space filling model is perfect for representing the electron density present in the molecule. Okay, so as you could see, for water, we could see the electron distribution that is represented by the red sphere, which is the oxygen. So it the electron distribution is large for the oxygen compared to the other hydrogen. Same with the ammonia. There is a large distribution of electron density around the nitrogen compared with the nearby or bonded hydrogen. Okay, so let's recall the Dalton's atomic theory. So for example, we have here the gray sphere represented as hydrogen, oxygen represented a red sphere, nitrogen represented a blue sphere, carbon represented as black sphere, and chlorine represented as green sphere. So let's look at the figure 2. As you could see, every carbon monoxide, it was defined that the carbon monoxide has one red sphere and one black sphere, meaning one oxygen and one carbon. So the ratio is 1:1. So for it was already defined. Carbon monoxide, there should be one oxygen, one carbon in each molecule. Another one is the carbon dioxide. So you could see there are two red spheres present, and one black sphere, meaning to say there are two oxygen and one carbon for every carbon dioxide molecule. Okay, one carbon is to two oxygen. So next one, hydrogen peroxide. So we have two gray spheres and two red spheres, meaning there are two hydrogen present and two oxygen present for every one molecule of hydrogen peroxide. Okay, 2:1. And next one, water. So you could see we have one red sphere is to two hydrogen sphere. So that is the definition of a water in terms of the number of hydrogen and oxygen molecules. So this figure pertains to the law of definite proportion. It states that a given chemical compound or a given molecule, it always contains its component elements in a fixed ratio. So for example, if you have one molecule of carbon dioxide, you always get one atom of carbon and two atoms of oxygen. So for that case, if you have two molecules of CO2, it means that you have 2 carbons and 4 oxygen. Okay? Next one, we have this carbon, 1 carbon, and there are 2 oxygen. So during a reaction, so this arrow represent the proceeding of a reaction. We will be having 3 spheres, 3 total spheres. So this one is the law of conservation of mass. So it states that the mass in an isolated system is neither created nor destroyed by chemical reaction or any physical transformation. So meaning to say, even if you proceed the reaction, perform a process, you will still maintain the total mass. So the mass of the reactants will still be equal to the mass of the product. There's no mass that is created nor destroyed. Okay? Next one, we will learn how to write a chemical formula using the ions. So we have here a metal. Metal is typically positively charged ion. So you will always see a metal as a positive ion and a non-metal on the second on the right side. So cation and anion. So cation positive, anion is negative. Okay? Cation or all metals are cation, so they will be always positively charged when they exist as ion. Okay? So we have here, we want to represent this combination of ion in an ionic compound, and we would like to present them in a chemical formula. So how we would write it? So as you could see, the charges, so charges, this one charges, this one is also negatively charged, positive charge, positive charge, and negative charge. Okay, so the charges is presented as a superscript in an atom. So to present them in a chemical formula, you just need to transpose the charge into the subscript of the opposing ion. So you place the superscript as a subscript. Same with the other charge in the right side. We place this charge as the superscript as a subscript of the another or the opposing ion. So for that case, we will be creating Mg2 plus Br1 minus by using the charge cross technique. You will be having Mg1 Br2. Again, subscript is non-negative. You don't need to write the negative sign on the subscript, because the subscript means the number or number of atoms. Meaning to say, if this is Mg1 as a subscript, it means there is one atom of magnesium. And Br2, it means there are two atoms of bromine. And for convenience, another thing to note is that we don't need to write 1. So you may remove the written number 1 here, and it is already understood that when there is no number beside the atom, it means that correspond to the value of 1. Okay, so next one, Li2O. For this case, let's try to identify the ions. So we will be performing the reverse of the charge crossing technique. Okay, so for that case, reverse lang from subscript to the superscript of the opposing atom. So again, it is understood that on the right side of the subscript of oxygen, there is a value of 1. That is already understood. So for that case, we will be having Li 1 and oxygen 2. Next one, we need to place the charge. So since 1 is charged, so a positive sign and negative sign is required. So which one of them will carry the positive charge? Which one of them will carry the negative charge? So for that case, in an ionic compound, the first element will always carry the positive charge. The first element will always carry the positive charge. Okay? And the following element or elements will carry a negative charge. So for that case, this one, lithium, is 1 positive, oxygen is 2 negative. Okay, so this one is our final answer. MgO. So this one is tricky one, no? So again, we will be doing charge crossing technique in a reverse manner. So we place the subscript here, we place the subscript here. So if you done it in the conventional way, so maybe you will think that since there are no values, that is Mg1 and O1, so when you perform the charge crossing technique, you will create Mg positive 1 and oxygen negative 1. So however, this is wrong. We recall that oxygen always carry a charge of negative 2. So that is a fixed definition in ionic compound. Okay, oxygen will always carry 2 negative. So I think you need to remember that. And what will be the charge of magnesium if this one is 2 negative? Recall that we have the 1:1 ratio represented in this formula, meaning there is 1 atom of magnesium, and 1 atom of oxygen, and their ions is equalized or neutralized, meaning if you add their charges, if you already know their charges, that is equal to 0. Okay, so to identify that, what would be the charge of magnesium if there is only 1 oxygen and 1 magnesium? So you need to find a number that when you add to negative 2 will be equal to 0. So obviously the answer is positive 2. Okay? So the charges of ions present in magnesium oxide is, or MgO, is magnesium 2 plus and oxygen 2 minus. Okay, let's try board work. So let's identify the chemical formula when the following ions were combined. So first one, Fe 3 plus and Cl minus. So using the charge crossing technique, we will be having Fe 1 Cl 3. Again, for convenience, we don't need to write 1 as a subscript, so we can write it on this manner, FeCl3. Okay, next one, Cu 2 plus and sulfur 2 minus. Charge crossing technique, 2 plus going to the right side, 2 minus going to the left side. So we will be having Cu2S2. However, in ionic compounds, we are required to write their subscripts in lowest term, so we can simplify their subscripts. So for that case, that will be Cu1S1 or CuS. Okay, next one, aluminum 3 plus and NO3 minus. Okay, so when you see this kind of an ion, there are times that an ion exists as more than one element. So meaning, if you have this NO3 minus, it means the charge is -1 was carried by not only by oxygen but also by the nitrogen. So it was carried by these whole ions or set of atoms. Okay, so for that case, still we're doing charge crossing technique. We place Al3 plus towards to the right side of the NO3, and the -1 will be carried out on the side of aluminum. For that case, that will be aluminum, that is -1, so we write 1, and 3 we place it on the side of the not only the oxygen but also with the nitrogen and oxygen ion. Okay, so NO3, we place them in a parenthesis to indicate that there are 3 units of NO3. So Al1 parenthesis NO3 parenthesis 3. So for convenience, we omit the 1, so that is AlNO3 3. Okay, another example. So for this case, we want to identify their charges. So NaCl, so that is obviously Na1Cl1. We perform charge crossing technique. Then we could identify that the charge of Na is +1 with our cation, since it is the left side element, and the Cl is -1. Al N. Okay, so as we recall, nitrogen always carry a negative 3 charge in ionic compound, so that is fixed. So N 3 minus. So there is a 1:1 ratio, meaning there is 1 aluminum and 1 nitrogen, and their overall charge, the sum of their charges, is equal to 0. So you just need to think a charge of aluminum, that is when you added it with the negative 3 charge of nitrogen, will be equal to 0. So for that case, that is positive 3. Okay, next one is Fe2SO4 3. Okay, so first let's identify which one is the cation. Obviously that is iron. Our cation, a single element, a metal, so that is iron. That means the remaining elements will be our whole anion. Okay, SO4. So we perform charge crossing technique. So we place 3 here. It means it would be Fe3 plus, since it is our cation. And SO4, we have 2 here. Charge crossing technique, we place it above the SO4. It means that overall charge of SO4 will be equal to 2 negative. Okay, so that's all for today. Thank you.